Hey everyone, Professor Mankowski here, and in this video we're going to go and take a look at Chapter 9 and Chapter 10. Chapter 9 is all about studying correlation between different variables. Now, what would we use correlation for? The answer is regression, which is Chapter 10. So regression is all about predictions. If you signed up for the statistics class and you were thinking, where am I going to get a chance to learn how to make forecasts into the future for what numerical values might be, what values they take on? The answer to that starts in the regression chapter. And the basic idea of doing regression, doing predictions, is going to be we're trying to figure out what the answer to a forecast is for something we can't see, a variable that we don't have any information on. So what we're going to learn how to do is base that on a variable that we do have information on. So it's as if we're going to use what we can see to tell us about what we can't see. If you're trying to figure out something like what would be my savings account next year, I might be able to base that on what I expected my income to be. If I was trying to figure out what's going to be my GPA in a few semesters from now so I could graduate with honors, I might be able to base that on something like how many hours a week I'll have to study. Maybe I'm the manager of a gym and I need to make sure that I have enough equipment available for people to come in and use when they're working. I might be able to base the number of hours they're going to spend exercising on how many hours people work each week. So when we're thinking about how we're going to predict something based on what information we have to work with, we get our first definition, dependent variable. So if we're going to go ahead and predict GPA, we might say that GPA depends on something like how many hours we studied. So we're going to refer to the hours studied, or the information we're using for our prediction, as the independent variable. Another example, maybe vacation budget. Everybody likes to go on vacation. So we might be able to base vacation budget on something like how much income a person is making. So income would be the independent variable that's going to help us predict the dependent variable of our vacation budget. And we'll do one more. The one we looked at for exercise time. Exercise time would be our dependent variable, and the number of hours a week somebody spends employed would be an independent variable. So if we just focus on one of these, maybe GPA, because that's something very relevant to us, we might wonder, are there more things that would predict the GPA than just the hours we studied? And absolutely, there could be lots of different things. It might be something like how many different classes you're taking at the same time, like the total number of credits you're taking, how many classes you attended of your statistics class. As we attend more classes, we would expect to have a positive effect on our GPA. Perhaps the number of hours we work each week on the job, because if we're working 100 hours a week, we're not going to have much time available for studying. If we're working a moderate number of hours, we would have more time for studying. And last might be something like income level. Maybe if we make more revenue, we have more money available for tutoring. So of all these different possible candidate independent variables, how would you figure out which one is the best? And the answer to that is we're going to start to look at something called a scatter plot matrix. What a scatter plot matrix is going to do is help us do a graphical plot of our dependent variable against our independent variable. So let's take a look at something like our GPA versus how many classes we cut. If we go ahead and we look at the number of classes cut versus our GPA, what do we tend to notice? Well, according to our graph, it kind of follows our intuition. As we start to increase the number of classes that we're cutting, what's happening to the GPA? It's going down, right? So if we start to look at some of our data values on the graph, we go ahead and we look at the upper left there. We're not cutting very many classes, so we would expect our GPA to remain pretty high up in that area. Now, as we increase the number of classes, what's happening to the GPA? Notice that it's starting to drop, right? Until we get to the very bottom, the extreme lower right, we've cut so many classes, almost 10, as if we're cutting every other week. This time, we're expecting the GPA to be very low. Now, let's take a look at another graph, maybe GPA versus the number of classes we attended this time. So here's our scatter plot. And this time, it's almost exactly the opposite. As we increase the number of classes we attend, we'd expect to understand more because we're there for all the professor's lectures. So we would expect the GPA to start going up, right? So in both of these two cases, we seem to have a very close relationship between our independent variable and our dependent variable. But let's take a look at a case where the relationship isn't so direct. Like if we consider something like our GPA against the number of classes we're taking in this semester. If we look at the sketch this time, it's a little bit more interesting because the relationship is not as direct. Notice our dots seem to be a little bit more scattered this time, don't they? And that might be kind of interesting to think about in the sense that we might know somebody that's only taking one class and they're getting an A in it. They're just taking one statistics class and they have A+ in that class. But we also know plenty of people that might be taking 4 or as many as 5 classes and they're getting A's in all of those. That's why we don't have as much as a direct relationship anymore. Now, let's take a look at one where there's even less of a relationship. We look at GPA versus weekly earnings. In this case, the dots are scattered much more farther apart, and it almost doesn't look at all like we could use somebody's weekly earnings to predict their GPA, does it? So if we end up taking a look at all the different graphs together, how do you know which scatter plot is the best one? Well, what we're going to do is look for the one or the graphs that have the strongest linear relationship. And that would be illustrated by the scatter plot up in the upper left here, because we're going to find the scatter plot diagram that has the closest to forming a straight line. Now, one thing we have to be kind of careful of is a lot of students will also tend to pick the graph in the lower right because they're thinking, oh, I can draw a line, only it's curved. And that's where we have to watch out, because if we're going to do eventually our chapter on regression, we have to make sure that the relationship is going to be a linear relationship, meaning it has to be a straight line. Eventually, when we get into other forms of regression and statistics too, then we'll start to learn how to work with shapes that look like they might be parabolas. For right now, though, we just want a straight line. Okay, if we go back to our scatter plots that we had before, it looks as though number of classes cut and number of classes attended might be the best candidate independent variables for us to use. But what if you had maybe 5 or 6 scatter plots and they all had pretty close to straight lines when you were looking at the position the dots were in? How would you figure out which one to use? And the answer to that is with something called a correlation coefficient, which we're going to soon call R. That's going to be the abbreviation. Now, first thing about correlation coefficient, the computation to calculate it out is fairly complex. So don't worry about calculating it out. We're going to concentrate on the interpretation. And first thing that we're going to think about is when we do the interpretation, a 0 would mean we calculated our correlation coefficient based on the values of independent and dependent variable, and the correlation coefficient computed out to be a 0. That means there's absolutely no relationship between the dependent and the independent variable. In other words, the independent variable we've chosen cannot be used to predict the dependent variable because there's simply no predictive properties. There's no quantitative relationship whatsoever between the variables. How about if we take a look on the far right? Strong positive relationship. This means that whenever there's an increase in our independent variable, there's an exactly equal proportionate increase in our dependent variable. When one moves straight up, when our independent variable moves up, our dependent variable always also moves up. An example of something like that might be closer to the number of classes that we're attending of a statistics class. As we would expect, when we attend more classes, our comprehension of our material would go up. Now, what about the opposite side of the expression, of the sketch? If we go to the far left where we're seeing the negative one, that means the relationship is a strong negative linear relationship. So as we increase the independent variable, the dependent variable is going to move exactly in the opposite direction. And that would be an example of something perhaps maybe like the number of classes we cut. As we're cutting more and more classes, we're expecting our GPA would probably go down because we're having so many gaps in our knowledge. We're simply not there for anything the professor has to say. So let's go ahead, let's take a look at some of the scatter plots that have correlation coefficient labeled in them, so we can analyze what this looks like. Now, our correlation coefficient on the bottom of the graphs is indicated with a lowercase letter r. So if we look on the positive, on the rightmost side, we have a correlation coefficient that equals 1. So whatever independent and dependent variables that we had, they were forming a perfect positive linear relationship. That's why our line is on a 45-degree angle. When the independent variable increases, we get an exactly proportionate increase in the dependent variable. Now, if we look at the graph in the middle, this one's a little bit different. Notice how we're at 90% and our dots are a little bit more spread apart this time. What that means is when our independent variable increases, 90% of the time, we're getting a corresponding increase in a dependent variable. So not a perfect 100% of the time, but 90% of the time. Now, if we go on the far left where we have our correlation coefficient at 50%, notice how the dots are much more widely scattered. And this time it means if we increase that independent variable, we're only getting a corresponding increase in a dependent variable 50% of the time. If we were to look at negative correlation coefficients, it would be a very similar situation. Okay. So all of this taken into consideration, let's take a look at how you would actually compute your formula for the correlation coefficient. Now notice the formula looks pretty intense, and this is why we're not actually going to calculate it out. We would most likely be using a Microsoft Excel at this point if we needed to calculate it out. But just to get an idea of how it does work mechanically, let's go ahead, let's take a look at a data set that's all about rental car companies. So if you're an investor and you want to figure out how much money a rental car company is going to make, what their revenue is going to be, that's a pretty important investment decision, right? So it might be a pretty logical idea to base their revenue on the number of cars they have available for rent, because we would think the more cars you have to rent, the more money you will make. So if we take a look at the first line of our data set, Company A, they had 63,000 cars, and their revenue was about $7 billion. If we drop down to Company B, notice that their car fleet is about half of what Company A's is. So clearly we don't expect the same revenue for Company B, do we? In fact, we're only getting roughly half the revenue we did for Company A, which tends to make sense. And if we look at the scatter plot tends to look like it has its dots coming pretty close to a straight line. So this would be a fairly decent set of prediction variables, a good independent variable for predicting our dependent variable. Now, how do you actually create the correlation coefficient? Well, we have to start by putting lots of extra columns in our data set, a column for the variable x, which is going to be our independent variable, and y, which we're going to call our dependent variable. So first thing that we're going to have to do is multiply x times y. Then we're going to have to add in another column for x squared, and then a column for y squared. When we get all of the totals of those different columns, then we have to start putting them in our formula. And our formula ends up giving us a 0.982, which means there's a 98% correlation between the size of the car fleet and the income level. So now that we have a really good idea of how to figure out what's the best independent and dependent variable combination to do our prediction using a correlation coefficient, how do you actually go up and set up a prediction equation? So to get there, let's go back to our data on the rental car company, and we're going to take a look at the scatter plot. What we want to do with the scatter plot is we want to put a line through the scatter plot that hits as many of the dots as we can. So if we propose our line is going to sit right there, what's going to happen is we'll get an equation for that line, and when we input a value for x, that would stand for the size of the car fleet in thousands. Like 5 would be a company that had a fleet of 5,000 cars. 8, a company that had 8,000 cars. the answer that we're going to get back in the equation is going to give us exactly our revenue for that size car fleet. Now, the idea makes a lot of sense, but there's one little problem. We were saying that we wanted to get a line in there that comes as closest to the dots as we can, but how do we know that's exactly where the line should go? Like, what if somebody else were to say, you know, that's the wrong line. It should really go in this place because now you're hitting more dots. And then a third person came in and said, no, that's all wrong. Here's where it should really go. Like, how would you actually figure out which line would be the best one? Now, statisticians thought about that, and here's what they came up with. Let's take a scatter plot that's a little bit more widely dispersed so we can see what needs to happen here. If we go ahead and we put a line through the center of the scatter plots arbitrarily, what we can do is we can start to measure the vertical distance between all of our dots and the line. Like we have distance 1, distance 2, 3, 4, 5, and 6. And what statisticians were able to figure out is that we would have the line in the correct position if it minimized the distance between all of the vertical spaces. Meaning the line that's going to be positioned the best is going to be the one that minimizes the vertical distances between all of the numbers, all the scatter plot dots and the line. So what would the line actually look like? Well, the equation is going to take the form of y equals a plus bx. And if we actually take a look at how we would fill this out, we go back to the rental car company data, we would call our dependent variable y, our independent variable x, and then we would have to compute out columns for x times y, x squared, and y squared, and go through those columns row by row. Now, once we get the sums of all the columns, we would have to fill out these next two pieces to come up with what A was going to be and what B was going to be in our equation. And I know this looks very hideous, but don't worry, you'll never actually have to compute the equation by hand or even on your calculator because it's so intense. In fact, if we were doing a regression equation, we would probably be using Microsoft Excel at that point because the calculations would become very error prone to do that on a hand calculator. But what we will practice is how you actually interpret the equation because that's really important in application. So if we look on the bottom of the screen, our equation is y prime, or y apostrophe, standing for our dependent variable, equals 0.396 plus 0.106x. So if we were to input a number for x, like, for example, 7, for a company that had 7,000 cars in its fleet, or 15 for 15,000 cars in the fleet, the value we get for y prime would be exactly equal to the revenue that we would expect to get for that size car fleet. And one other thing that we can do that's really cool with the line, notice how the coefficient from the x term is 0.106. What that means is if we increase the fleet of the cars by 1,000, we're going to expect an increase in revenue by about $0.106 billion. And this is going to be our summary for how we construct simple linear regression equations.